Okay, so in this video, we're going to go over those recommended practice problems at the end of lesson 8.1. This is the lesson on overlapping quantifiers. Those problems were page 295, 3i, and then page 296, 4a, 4c, 4e, and 4g. Now, I didn't realize when I assigned these problems because I hadn't worked through them recently, but 4e and 4g each include a typo. They both include the number 1 as like a specific referent, but there's no 1 in your symbolization key. So what we're going to do is we're just going to turn that into a 2, which is what's consistent with the solutions in the solutions manual for the textbook. So I apologize if you tried to work through those problems and got confused. We're just going to change that 1 to a 2, which I believe is what was supposed to happen in the book. Unfortunately, textbook editors miss things and things like that happen all the time. So let's go ahead and get started with 3i, right? This is from that set on the seniors of Dartmouth College. Our sentence is, everyone who becomes a longshoreman will make more money than everyone who does not. So here we have 2 instances of everyone. We're going to be involving 2 universal quantifiers. And the structure of this sentence doesn't really give us a lot of indication of what we're going to be doing. But the way that we should think about this is if one person becomes a longshoreman and the other person does not, then the first person will make more money than the second. So the way that we paraphrase this is for every x and for every y, if x will become a longshoreman and it's not the case that y will become a longshoreman, then x will make more money than y. So we have to have those 2 separate quantifiers to be talking about someone who becomes a longshoreman and someone who doesn't to compare them. And we will be using a material conditional in the scope of those quantifiers. So we're saying for every x and every y, if an x becomes a longshoreman and the y does not, then x will make more money than y. And now I want to go ahead and put in parentheses. So I've put brackets around the whole sentence after those quantifiers. That's to make sure that every occurrence of x and every occurrence of y are both in the scope of those quantifiers. We start here, right when we get to the if, we already have an x, and then at the very end we have a y. So that whole thing needs to be in parentheses, or as I've used, the square parentheses, the brackets. Now you don't need to double up here. One set of brackets works fine and indicates that it's in the scope of both of these quantifiers. And then I've done a second set of parentheses around that antecedent, right? We've got an and here. The antecedent's a conjunction. X will become a longshoreman, and it's not the case that Y will become a longshoreman. So the completed symbolization looks like this for all X and for all Y. If X becomes a longshoreman and it's not the case that Y becomes a longshoreman, then X makes more money than Y. Everyone who becomes a longshoreman will make more money than everyone who does not. So any 2 cases where you pick an x and that x is a longshoreman and you pick a y and that y is not a longshoreman, then the consequent is true, x makes more money than y. Now let's move on to the second set of problems. Here we're talking about integers, right? We're talking about numbers, and we've got this symbolization key. Again, the only individual constant we have is 2, which is why we have to change problems E and G because of the typo. But let's start here. There is a positive integer that is less than all primes. So here we've got a there is a. We know we're going to be using an existential quantifier, and that is less than all primes. So we're going to need a universal. Here we can see by the form of the sentence that existential quantifier is going to come first, right? It's important that we have this right, that there's a single positive integer that is less than all primes, so that existential quantifier comes first. If we reversed it, then we would say for all primes there is some integer that's less than it. So our truth functional paraphrase is there is an x such that for every y, if y is prime, right? Because we want to say that positive integer is less than primes. We need to make sure when we specify this, we're using the y or the same variable we used in the universal quantifier. Then x is less than y. So there is such an x that for everything that's prime, x is less than y. So this is also a conditional. Even though the existential is in front, we are saying that all primes are greater than x, so we're still going to use that conditional because we are still within the scope of a universal quantifier. For parentheses, we're just going to put that whole thing in the scope of those quantifiers, right? We have the x's in the consequent and the y in both the antecedent and the consequent. We need to put the whole thing in that scope. Now, you couldn't have said something like, for every y, if y is prime, then there is an x that is less than y. That would have said something different. That would have said, for every prime, there is a positive integer less than it. So it's important that we have things in this order to capture this meaning. So the symbolization looks like this, right? There exists an x such that for all y, if y is prime, then x is less than y. There's some positive integer that is less than everything that is prime. For C, a prime times a prime is not a prime. Now these ones can be a little misleading because we have a prime, right? That might sound like we're using an existential quantifier. But this is more specifying a rule about how things work, where we're talking about any arbitrary prime. Here's a different example. If I say something like, a student needs to do the graded practice to get a good grade in this class, right? I'm not just talking that there is some particular student that would need to do the graded practice to get a grade in this class. I'm saying if we take any student, right, a student in this class at all, then you need to do the graded practice to get a good grade. So we are going to be using universal quantifiers here. And we're going to need two, because what we're saying is any prime times any other prime is not going to be a prime. So the truth functional paraphrase looks like this. For every x, for every y, if x is prime and y is prime, then it is not the case that x times y is prime. Hopefully this makes sense. Because we need to capture a prime times a prime, right? Any prime, if we have any prime times any other prime, then when we multiply them together, it's not going to be the case that that result is prime. And using our symbolization key, and here we have the scope lines, or the brackets, right, to indicate the scope of those quantifiers. We need to put the whole thing in the brackets for the quantifier scope, right, because we have x's and y's in the antecedent and the consequent. So we need to make sure that these x's and y's in the consequent are also in the scope of that quantifier. And then we need parentheses around the antecedent because the antecedent's a conjunction, right? If x is prime and y is prime. So here's the symbolization. For any x, if x is prime and it's multiplied by any y that's also prime, then it's not the case that x multiplied by y is a prime. Okay. Here I have 2 in bold because I edited this. The original problem said 1. There's no 1 in our symbolization key, so we don't have a way to symbolize that. A prime times any positive integer greater than 2 is not prime. Now this is really similar to the last one, right? The last one said a prime times another prime is not prime, and we did both of those specifications, that one is prime and that the other is prime in the antecedent, and then we had the consequent that them being multiplied together is not prime. It's not the case that that multiplication is prime. So here we're going to do the same thing, except we're specifying that 1 is prime, right, for every x, if x is prime. But for y, we're specifying that 2 is less than y. The original problem says a positive integer greater than 2, but we don't have a greater than predicate in our symbolization key. So what we do is we use the less than predicate and reverse it, right? If the positive integer y is greater than 2, then 2 is less than y. And then our consequent here is the same as the last problem. It's not the case that x times y is prime. Our brackets here and parentheses look exactly the same. We've got parentheses around the antecedent, since it's a conjunction, and brackets around the whole rest of the problem to put them in the scope of the quantifier. So the only difference between this problem and the last one is that instead of saying y is prime, we say that 2 is less than y. And the last problem. So this one has a lot going on, and it's much more in depth than anything I'm going to assign you on an exam. This is a much harder problem, but I think it's good to look at some of these complex ones and learn to break them down and not stress about it. So here we have, if a pair of positive integers is such that the first is evenly divisible by the second, and the second is greater than 2, then either both are even or both are odd. So the way to break this down is to use the universal quantifiers and variables and slowly work through it, right? So we know we're going to be saying for every x and for every y, and then we need to capture these specifications about the first and the second. And we're going to be using a material conditional, right? This has if-then already built into it. So here's the first half where I only capture the antecedent, right? For every x and for every y, I've made x the first, right, from the original sentence. So the first is evenly divisible by the second becomes x is evenly divisible by y, and the second is greater than 2 becomes 2 is less than y. Okay, so now let's look at that consequent, either both are even or both are odd, right? We need to break that down into x's and y's and predicates and all of that stuff. So we get then x is even and y is even, or x is odd and y is odd. And here we have parentheses around each conjunct, right? Both are even or both are odd. The or is the main connective of this consequent. We have the second set of parentheses here to put the consequent together, right? That whole disjunction. And then we have the closing brackets for the scope of those quantifiers, right? To make sure that we have the entire material conditional all the way through the end of the consequent in the scope of the universal for x and the universal for y. So every occurrence of the variables is in those scopes. And then our symbolization looks like this. We get for all x and for all y. If x is evenly divisible by y and 2 is less than y, then x is even and y is even, or x is odd and y is odd. And like I said, this is a much harder problem than anything I'm going to give you on an exam, but I did want to work through it just to give you a better picture of how to break these problems down and look at them. So that's it for this review. Hopefully this was helpful to you with working on problems on your own. And next time we'll be moving on to talking about involving something called the identity predicate.